Now, we've considered the frictionless case for an inclined plane, and we've seen that if we have some object with some mass m on the plane, it will accelerate down the plane if there is no friction. It's got a weight force going vertically downwards, which is given by mg, and we can split this weight force into two components: a component parallel to the plane given by mg sine theta, and a component perpendicular and down into the plane given by mg cos theta. And then we've got the normal reaction force to that weight force, which is also given by mg cos theta, but it's in the opposite direction, up and out of the plane. And as a result of those forces, our object accelerates down the plane. However, often when we're considering inclined planes, we can't neglect friction. There usually is some friction involved, such as in this case here, there must be friction, as the net force on this body must be 0 because it's not moving. So we've still got the same weight force and the same normal reaction force in this case, but in this case we've also got some friction that we'll need to account for. So let's once again consider an object with a mass m on an inclined plane, and we'll suppose that the coefficient of friction between the object and the plane is given by μs for the static case and μk for the kinetic case. So let's start by considering the static case, such as this case here, and we'll try and come up with an expression for the frictional force which is acting in this case, and then we'll also consider the conditions for which the block will start to slide down the slope. So if we can increase the weight force down the slope by increasing the angle, at some point our block does start to slide, so we'll come up with some expression to describe that point. Okay, but first of all, the case where it's at rest. If it's at rest, we know that there is no net force acting on it, so the components perpendicular to the plane and parallel to the plane must be equal to each other. And so we've already seen that the normal reaction force is mg cos theta because the weight force perpendicular to the plane is mg cos theta. So let's consider what happens in the parallel case. In the parallel case, we've got the component of the weight force mg sine theta going down the plane, and so to counter that, the frictional force must be pushing it up the plane. So the frictional force is opposing the net force on the system, like it always does in the static case, and so that force up the plane must be equal to mg sine theta. Okay, now let's consider when it's going to start moving. So for it to start moving, the weight component down the plane must be bigger than the maximum possible static friction force. So we've seen that the maximum possible static friction force is given by μs times n, where n is the normal reaction force. And in this case, we've said the normal reaction force is given by mg cos theta. So we need our component of the weight force down the plane, mg sine theta, to be greater than that maximum possible frictional force, μs times mg cos theta. So the angle at which this starts to happen is going to be when these two expressions are absolutely equal to each other. So we can find the angle at which mg sine theta is equal to μs times mg cos theta. So looking at this equation, we can see there's an mg on each side. So the mg's all cancel out and we end up with, well, sine theta is equal to μs cos theta. So we can rearrange this and say, well, μs is equal to sine theta divided by cos theta. But just using some trigonometry, we know that sine theta divided by cos theta is actually tan theta. So we can say, well, the angle at which it starts sliding, theta, is going to be given by the inverse tan of μs, where μs is the coefficient of static friction for this case. So you can actually measure this for different surfaces by varying the angle and measuring the angle at which it starts to move, and from that you can calculate μs. Now we should also consider the kinetic case. So for example, once it's moving and I know my kinetic friction coefficient is given by μk, well, what's the frictional force in this case? Well, with kinetic friction, it always acts in the opposite direction to the motion of the system. So it always acts in the opposite direction to the velocity. So in the case where my object is moving up the slope, so the velocity is in this direction, then the frictional force is down the slope. So it's parallel in this case to the component of the weight force. The size of the frictional force is given by mu k times the normal reaction force, and the normal reaction force is just mg cos theta. So we've got that frictional force is equal to mu k times mg cos theta. Now in the case when it's moving down the slope, the frictional force opposes this motion. So the frictional force is acting up the slope while the component of the weight force is down the slope. Now it is possible with Tracker to do a little experiment with your students where you measure the coefficient of kinetic friction for a ramp and a box. So what you do in that case is set your ramp to some angle such that the box is moving. Push the box up the slope and let it come back down, and you can measure the velocity and the acceleration of the box, and from those you can calculate the coefficient of kinetic friction. So let's have a look at a couple of example problems now, and then we'll come back and look at this in a little bit more detail.
So the question is, a 0.500 kilogram box slides up a ramp with an initial speed of 3 meters per second. The ramp makes an angle of 20.0 degrees with a horizontal. The coefficients of friction between the box and the ramp are mu k is equal to 0.200 and mu s is equal to 0.250. Part 1. What frictional force acts on the box? Part 2. How far along the ramp does the box slide before coming to rest? And part 3, what speed does the box have when it returns to its starting position? Okay, so let's draw a little diagram because that's always a good way to start. And so we've got an angle here, theta, which is 20 degrees. We've got a mass on our ramp. Initially, it's traveling upwards with a speed v is equal to 3 meters per second. And acting on this mass, we've got the weight force, mg downwards, which we can break into two components. We have mg sine theta pulling it down the slope, and mg cos theta pushing it into the slope. So we've also got our normal force, which is going to be the same size as this mg cos theta force. So N is equal to mg cos theta. And then we've got our frictional force, and the frictional force opposes the motion. So the frictional force is going to be down the slope in this case, in the direction of that purple arrow there. And the frictional force, it's moving, so it's kinetic friction, so it's given by mu k n, and the normal force we've just said is mg cos theta. So this is equal to mu k times mg cos theta. Okay, so in part 1, we're asked what frictional force acts on the box. So we can now calculate it because we've just said, well, our frictional force is equal to mu k times mg cos theta. And we have values for these. So we've got 0.200 times the mass, which is 0.500, times 0.980 times cos of 20. So we can put all that into the calculator and we end up with 0.921 newtons. And in this case, the direction is parallel to the plane and down it. So down the slope. Okay, let's scroll up to give ourselves some more room. For part 2, we're asked how far along the ramp does the box slide. Okay, so in order to answer this, we're going to need to make use of our kinematic equations. They apply because the acceleration is constant in this case. It's different for if the box is moving up or down the slope because the friction acts in different directions, but for either one of those cases, it is constant. So in order to find out how far it slides, we can use the equation v squared is equal to u squared plus 2as. And we know that v is equal to 0 because we're trying to find out how far it goes before it comes to rest. So at the end, the final velocity v must be 0. And u, we were told that the initial velocity was 3 meters per second. And so we can rearrange this, and we have the distance it goes is equal to u squared over minus 2a. So what we need in order to solve this is to calculate the acceleration. So in order to calculate the acceleration, we can use Newton's second law, which tells us that the sum of the forces is equal to ma. And here we only need to consider forces parallel to the slope, because perpendicular to the slope we know that the normal force counters the weight force. And so the forces which we will be considering in this case are the frictional force, which is acting down the slope, and the weight force, mg sine theta, the component of the weight force parallel to the slope, which is also acting down the slope. Okay, so we've already calculated the frictional force up here. So we have ma is equal to 0.921 plus mg, which is 0.500 times 9.80 times sine 20. Okay, so when we find that on the calculator, we end up with a force of 2.597 newtons down the slope. So our acceleration is just this 2.597 divided by the mass, which was 0.500. So this is equal to 5.19 meters per second per second. Okay, so now we have the acceleration, and we can go back to our equation here to get the displacement. So it's u squared, which is 3 squared over minus 2 times, now this is minus 5.19, as this force is acting down the slope, and this velocity was up the slope, so they're in opposite directions, so they have opposite signs. So solving this on the calculator, we have 0.866 meters. So that's how far up the slope it goes before it comes to a rest. Okay, so we shall scroll up now. For part 3, we need to work out what speed does the box have when it returns to its starting position. Okay, so for part 3, we're now considering the box coming down the slope, and the initial speed is equal to 0 because it's starting from this point, and we know the displacement is equal to 0.866 meters, and that's down the slope, it's displacing down the slope. So because it's now coming down the slope, the frictional force will be up the slope as it's going to oppose this motion here. The weight force is still down the slope, so we've still got mg sine theta down the slope, and perpendicular to the slope, they completely cancel each other out. Okay, so what we want to find is the final velocity v. So we can use v squared is equal to u squared plus 2as. U, we've said, is 0 because it's starting from rest. So what we're going to need to do is find the acceleration in a similar way to in part 2. Okay, so the sum of the forces, in this case, we've got the mg sine theta pulling it down, and then we've got the frictional force pulling it up. So they're acting in opposite directions, so one needs to have a negative sign. So the frictional force is given by mu k times mg cos theta. And from Newton's second law, we know that this is equal to ma. So we can cancel out all our m's, and we have a is equal to g sine theta minus mu k g cos theta. And so this is equal to 9.80 times sine 20 minus 0.200 times 9.80 times cos 20. And solving this on the calculator, we end up with an acceleration of 1.51 meters per second. Now at this point, we should just do a sanity check. We'd expect now, because the frictional force is opposing the motion, that the acceleration is smaller than it was when they were both acting in the same direction. And indeed, we do have a smaller value than we had in part 2 for the acceleration. So that's good. Okay, so now what we're trying to do is work out the speed when it gets back to its starting position. So now we can substitute into our kinematic equation. So v squared is equal to 2 times 1.51 times s, and that's the distance, so that's 0.866. And so v squared is equal to 2.62. So that tells us that v is equal to 1.62 meters per second, and that is going down the slope. So that's how we solve that problem. Let's have a look at a slightly different problem now. Okay, so our second problem is a horizontal push force F is applied to a block of mass M on an inclined plane. The coefficients of friction between the block and the plane are μs and μk. The block remains at rest. Part 1, what is the net force on the block? Part 2, what is the normal reaction force? Part 3, what is the magnitude of the frictional force? Okay, so part 1 is fairly easy as the block remains at rest, and we know that a body at rest will remain at rest unless acted upon by an unbalanced force. So it's remaining at rest, so there is no unbalanced force, so the net force is 0. Part 2, what is the normal reaction force? Okay, so let's draw all our forces on this block. So we've got the weight force, which is acting downwards, given by mg, and we can split this into two components. We can split it into a component parallel to the slope, which is given by mg sine theta, and perpendicular, that's mg cos theta. And this angle in here is theta, when this angle down here is theta. Now, we can also do the same thing to our force F. So force F, we can split into a component parallel to the slope. So parallel to the slope, up like that. So these are parallel lines, and then this line here is parallel to that. So the angle between these two is theta. And we've got a component perpendicular to the slope there. So parallel to the slope, we've got, this is F cos theta, and perpendicular to the slope, we've got our F sine theta. So why that's helpful is now we've got our two components perpendicular to the slope. There's F sine theta down into the slope, and there's mg cos theta down into the slope. And we know that because it's not moving perpendicular to the slope, all the forces must sum to 0. So we've got a normal reaction force up like this, and that must balance out our F sine theta and our mg cos theta force. So we've got that our normal force is equal to F sine theta plus mg cos theta. Okay, now part 3 asks us what is the magnitude of the frictional force. Now, this one, it's easy to get confused over. It's actually quite simple because the net force is 0. So parallel to the slope, the force is 0. So the frictional force must be equal and opposite to the other two forces. So just like the normal force had to counter out the other two forces. So in this case, we've got F cos theta pushing it up the slope, and we've got mg sine theta pushing it down the slope. So the frictional force must be F cos theta minus mg sine theta, and this is down the slope. So if F cos theta is really big, then the result of this will be down the slope. If F cos theta is really small and the mg sine theta is bigger, then we'll end up with a negative answer here. So that would be a resultant force up the slope, because the frictional force is going to counteract the net force on the system. So in this case, we didn't actually have to worry about our coefficients of friction. We could consider the maximum possible angle, in which case it does get quite complicated. And in that case, the maximum static friction force is given by mu s n, and we've calculated n in part 2, so it will be equal to mu s times f sine theta plus mg cos theta. So if we wanted to work out our maximum angle, what we'd need to do is set our frictional force equal to this maximum, so we'd end up with f cos theta minus mg sine theta is equal to mu s times f sine theta plus mg cos theta. And so if we divide everything through by cos theta, then we have f minus mg sine theta divided by cos theta, that's tan theta, equals mu s, and then plus f, now sine theta divided by cos theta, that's tan theta, plus mg cos theta divided by cos theta gives us 1. And so moving everything with a tan theta over to one side, we end up with mu s f tan theta plus mg tan theta. And then we've got f minus mu s mg. So I can take tan theta out as a common factor here, and we've got mu s f plus mg. And so tan theta is equal to f minus mu s mg over mu s f plus mg. And so theta is equal to the inverse tan of f minus mu s mg over mu s f plus mg. So given a certain f, that will tell us at what angle the block will start to slide.